maximize the GoToWebinar window from the option shown here. If you have any questions during the webinar, you can always type in the chat box or the questions window, and I'll be answering to those questions during the webinar. Okay, so in today's webinar, we will be looking at the introduction to the finite element analysis software, basically how to do finite element analysis using the different steps involved in the software. And then we'll look at some simple examples like 2D truss, two-dimension statically indeterminate frame, buckling analysis, and we'll also look at 3D structures, 3D frames, and then we'll go towards lateral torsion buckling of a beam. Okay, so for any finite element software, today we'll be focusing on MIDAS Gen. For any finite element software, we idealize the structure, or we call it modeling. The modeling is done based on dividing the structure into nodes and elements. So if your structure involves frames, then it will be idealized as line elements. If your structure has slabs or walls, they will be idealized as plate or shell elements in the finite element model. And if you have a 3D volume, they will be idealized as solid elements, which are basically tetrahedral or hexahedral elements. Now, the line elements that we will be focusing on in today's presentation involves beams and truss elements. So as shown on the screen, the truss elements have two nodes, and they support only the axial forces. So you won't be getting any other degrees of freedom, forces in any other degrees of freedom. So they only present you the axial forces, whereas the beam element has 6 degrees of freedom for each node. So you have 12 degrees of freedom for the one beam element, and you will get all the 6 components of forces as output for a beam element, which involves axial force, shear, moments, bending moments, and torsions. As you can see on the diagrams here, you have something called ECS, which is the element coordinate system. So as we go on in this in the demonstration, we'll look at how we can view results on a particular element coordinate system. So we have to keep this in mind. Plate elements, for modeling of slabs and walls, we divide the slab or wall panels into very small finite plate elements, which can be either triangular or quadrilaterals. So as shown in the figures here, you have 3 nodes in one plane, and connecting them you have a triangular plate, and similarly we have a 4-noded plate element here. Again, for plate element forces, we go for the we should keep in mind the element coordinate system. Every plate element has its own local coordinate system. Now the workflow for any finite element analysis that involves basically geometry creation, where we can create nodes and elements, the outline of our model in the modeling interface. We can also bring in models from AutoCAD. So the students who are more familiar with the AutoCAD type of modeling, you can generate the model in AutoCAD and bring in the software for analysis. Now then once we define the geometry, we assign the geometry or the lines or elements with materials and section properties. Then we define boundary conditions, which involves our fixed, pinned, or roller supports, and sometimes releases for creating pin joints. Then we apply loads on the structure, which can include a multitude of load types, like you have uniformly distributed loads, temperature loads, moving loads, pre-stress on the beams. So there are different types of loads you can apply. And then if your structure involves construction of a stage-by-stage construction, then you can also simulate such type of stage-by-stage construction in your analysis and see the finite element results, analysis results for each construction stage. So, but that is again optional because we do it for very special structures only. Then once we have entered the model data, we perform the analysis and extract the results. The results mainly include reactions, displacements, forces, stresses, and if you're doing some kind of vibration analysis, maybe if you're doing a buckling analysis, then it also involves the different modes of buckling and modes of vibrations. And finally, design. Well, this is not supported by all finite element softwares, but yes, the design is important, and we can generate quick steel and concrete member designs in the MIDAS software, which we can go through in the demonstration. Okay, so first example which I'll talk about is the 2D truss analysis. So we'll take the simple pin jointed truss as shown in this figure, and the elements involved will be truss elements as we discussed a few slides ago. Truss elements are elements which are basically pinned at both ends and only support the only give you the actual force components. Boundary conditions for this bridge simply supported, so pinned at one location and you have roller at the other location. And then we have loads applied as point loads as shown here. And for all these examples which I will be covering today, we have created the manual calculations as well, so which we will be sending out to you after the webinar, the link for all those documents. So typically for this type of truss, we use the method of sections or the method of joints for calculating the forces. So let me take you to the software and show you how to generate this truss. Okay, so here I have the software open in front of me, and an existing truss model is there. So that's how the interface looks, and as I'll be modeling the structure from the scratch, I'll be explaining you the different options. So to create a new project, we go to File, New Project here, and you get a blank screen like this. You can switch from different views, like right now it is in the isometric view. I can switch to the top view here and look at the coordinates. So X and Y are the horizontal axis of MIDAS Gen, and Z is vertically upwards, and everywhere the software follows the right hand rule for the coordinates. Okay, so we start with setting up the type of the analysis. So this is a two-dimensional analysis, so the structure type should be a two-dimensional structure. So we go to model structure type and we specify the planes in which we will be working. So basically the XZ plane, Z being the vertical and X is one of the horizontal axis. So click OK, and now we can model the structure in the two-dimension mode. Okay, so we start by creating a single point or a single node. So nodes, create nodes, and we generate a node at the origin 0, 0, 0. So we have a node here. Now I'll just change the background of the window so it's more clear. So all the display tools are available from this particular box or icon. You can go to display option and color and just change the background to white. Okay. Okay, so we have got one node here. You can display the node number by clicking on this option. So we've got node number 1. Okay, now we'll generate an element out of it. So model elements and extrude. Okay, so our the truss has a diagonal member AB. So we'll start with this particular member first. So that's 2 meters and 2 meters horizontally. So we'll enter 2 in the X and 2 in the Z direction, and use the selection tool here to just simply highlight the node and click apply. I'm just changing it to the front view. Okay, so that's the diagonal element. Let's see. So the next one is we have 3 meter at 3 meter height, and the distance is 4 meters from B to D. Okay. So so it's 1 meter from this particular node, 6 and 1 meter high. Apply and okay. And then repeat the same process downwards. So this time -1, and again here 2 and -2. Apply. Yep. Now we'll draw the horizontal beam. So select the node here, and as we see in this figure, we have 3 divisions, 3 bays. So what we will do is simply mark number of times as 3 and just enter 4, 0, 0, and click apply. So that creates the beam with 3 divisions. Now we just simply need to connect the points here to create the internal members. So we go to Model, Elements, Create Elements, and make sure we have truss selected. So truss, because we will be using the truss type of element. So truss has been selected, and just simply snap on the points here. This. Okay, and we have got the major outline of the center lines of the truss. Okay, now we need to also make sure that everything is actually of truss type. Otherwise, we will have some moments generated, which we don't want because it's a pin jointed truss. So you can check it very easily from the works tree. So on the left side, you have a tree menu which describes the model itself. So how many nodes you have, you can also always double click to highlight them. What are the truss elements? So truss elements are these. Beam elements, these are the beam elements. So we can change them into truss elements. So just when you highlight them by double clicking, you can just simply go to Model, Elements, and change element parameters, and say element type general beam to truss, and apply. So now all are truss elements. So that's how you change the element type or parameter of a given element. Now you need to make sure that when you are applying loads on this structure, since every element is of truss type, so any load that is applied on this structure should not produce any moment on these truss elements, otherwise the analysis might fail. So so that's the reason why all the loads are applied at the joints only as point loads. Okay, now we will define some material and section properties for the finite element analysis. So we go to Model, Properties, Material, and select Add. You can select any material we want. So if it's steel, you can go through the list of codes here. So British Standard, and you can select steel as 355. You can also define user-defined materials by clicking None, and you can specify the material properties here itself. There are other options like concrete and composite sections, SRC, and also you have user-defined sections. So these are similar. You can select the code and specify the grade of steel or concrete you want to use. Then comes the section properties. So you can access it by just clicking on this tab here, or you can just go to Model, Properties, Section, Add. And since this is a statically determinate structure, so the section shape will not affect the force results. So we can go for any section shape basically. So we'll go for a simple solid rectangle and say take it 0.5 by 0.5 meters. Give it a name. So section 1. Okay. If you click on Show Calculation Results, we can look at the different section properties like area and moment of inertia, and just click OK. So once you click OK, the section shape will appear on the screen. You can choose to display or undisplay that from this option. Okay. Okay. Now we define the boundary conditions. So go to Model, Boundaries, and go to Supports. So let's go back to the drawing and see what kind of boundary conditions are there. So here we have a roller at point C, and at point A we have a pinned support. So let's see how to apply those supports. So I just went to Boundaries and Supports option here, and it asks me to enter the directions to restrain. So for this particular node, I'll just highlight this first and make sure it's pinned. So for pinned supports, we need to restrain the horizontal X and the vertical Z. We don't have to worry about Y for this case because it's a two-dimensional structure. So everything is in XZ plane. So select DX here and DZ here and apply. So that's your pinned support. And for this particular node, we just highlight this and just mark DZ vertical, so it can roll horizontally, and click apply. So that's how we apply supports on a structure. Then we will apply the loads. So that comes under the load option. Let me just quickly save this model. So the software automatically prompts you to save at every 2 or 3 minute intervals, so you don't lose your data. So you go to Loads and Static Load Cases, and here we need to define some names for our loads. This is important because the software finally gives you the result based on these load case names. So for each load case name, it will give you the results in a separate dialog box. So we write in the name. So let's say this is so just name it force here, and just make it a user-defined load. Add. Close this, and now since we have entered the name, we can assign values to these loads. So I'll just go back and check the values that we want to enter. So 21 kilonewton at point C here, and 6 kilonewton horizontally at the point F. So go to loads, and since these are point loads, and points can also be are also referred to as nodes. So basically these are nodal loads. So we type in we select the load case name force and enter in the FZ category -21, and select this particular node here. Minus because it's in the vertically downward direction, so that's why -21, and we click apply. Similarly, we select this particular node and we change FZ to 0, apply FX 6 kilonewton, positive because it's from left to right, and apply. So you can see the arrows represent the two different loads applied on the joints. And now we have applied the loads. We can just click on the analysis button to perform the analysis. So you can just click on this button, or you can go to analysis and say perform analysis. Okay. So the analysis is performed. You will see a series of messages being displayed in the message window here. So if there are any warnings or errors in the modeling, they will appear up here, and the analysis will stop in between. Okay, so now we'll look at the results. So we'll just I'll hide this section shape. Okay. You can look at the element numbers as well. If I display the element numbers, this is the option used for element number display. So these are your element numbers. It's good to sometimes refer the element based on its number. So we go to results and we look at the axial forces. So our aim is to find out which member of the truss is in compression and or in tension. So we go to truss forces, select the load case name. So as I was saying, we need the names to be specified for the load case, because results are displayed based on the load case names. And we can choose to see the deformed shape of this truss and compare it with the undeformed or original shape, and look at the values. So just turn on the values here and say maximum apply. Just hide the element numbers. So these are the force values, the actual force values on each element. Minus indicates the compression, and positive forces indicate the tension. Okay, so if I say compression, so it will just show me the compressive forces only. So you know these elements are in compression, and these are the elements which are in tension. And in the background, the gray line indicates the undeformed shape, the original shape, and the one which you see here is the final deformed condition. Now you can choose to animate this structure and see how the deformation is actually occurring. So you can just press on animate, apply, and record. You can save this as a AVI file, and it's good for presentation purposes as well. Okay. Then the other thing which we are interested here also is the reactions. So you can go to results, reactions, reaction forces, and look at the reactions Fx, Fy, and Fz, which are reactions horizontally and vertically. So these are your reactions. We had pin support and roller here, so we get horizontal reaction at the pin support, which is equal to the force applied at this particular joint, and then we have vertical reactions as well. To see any result in a table format, we have the result tables option. So we can quickly go to any particular result type, say reactions for instance. Just go to select the force type or the load case type, click OK, and it will show you the reactions in a table format. Again, this particular table is Excel compatible, so you can just right click and say export to Excel, or just simple copy Control+C and paste in Excel. Okay, so that's how we do a simple truss analysis in the software. Now we look at some other examples. If you have any questions, please type in the questions window and I'll be able to answer you. Okay, so next example is the statically indeterminate frame analysis. So the last example was a determinate structure, so it was easy to do the calculations even by hand for such structures. But now we go towards the statically indeterminate frame, which has varying material and section properties, and also three supports, pin supports on the columns here, and some different types of loads being applied, like settlement, the supports settle, and then you have a uniformly distributed load applied laterally. You can say it's like wind load. Okay, and the purpose of this particular exercise is to calculate the final reactions, calculate the bending moment diagram, and look at the deformed shape because of the settlement. Okay, so just to mention here, if you want to do it manually, then we have different types of methods which involve strain energy methods and moment distribution methods, moment area methods, which can be used to calculate the force diagrams for indeterminate structures. But it's much quicker to do it using the finite element software. So we'll see how we can look into this problem. Okay, so again, I'll just open up a new project. So just file new project and just quickly create. Now here, since this is a rigid frame, so we'll use the beam elements, which allow for rotation and translation. So basically moments, axial forces, shear forces, all kinds of forces we will be interested in. Okay, so just I'll keep a note of the dimensions that we need for this example. So we have a beam which is divided at 2 meters intervals and 4 meters and 2 meters here. Okay, so I will start with we can start creating the model from create nodes and then creating lines out of those nodes, or we can use the structure wizard, which is a very quick way of modeling a beam. So I'll just show you. So we go to structure wizard beam. You can simply enter the distances. So our top beam has 2, 2, 4, 2 meters, and just click on add. Okay, and it will generate a beam, and you can just specify material and section as 1 and 1 by default. We can specify material and sections later on, so I'm just leaving it as a default number and click OK. So that's the top beam, and now I'll drop the columns from points B and C. So that's 6 meters and this one is 4 meters. So select this particular one first and model elements extrude and say in the Z direction -4, apply, and for this particular column -6 and apply. So that's the model generated. Now we'll focus on the material properties. So we see that we have the same materials in sections for beams AB and BD, that is EI, and BC and CE have 1.5 times EI. So and our EI is equal to this value as shown on the screen. So what we will do is we'll assume a value for E, and we'll just keep the I, or the moment of inertia, as 1 or unity. So we go to model, properties, material, add, and just to make sure that we are entering the values in the correct units. So we have in kilonewton per meter square. So to change the units anytime in the modeling process, we have the units bar here, force and displacement. And we can go to model, properties, material, add, and select user defined, say material 1, select 102.5 times 3, 10 to the power 3. Okay, and rest everything we can keep as 0 and just apply. Then the next thing is sections. So just go to section, add. Now we want to define a user defined section, so we will specify the properties manually. So instead of defining a shape and asking the software to calculate the properties, we'll go to value type and say select solid rectangle, and doesn't matter, we can keep the shape as 0. We are only interested in the properties. So we'll go for IYY, which is the the moment of inertia about the major axis. So we type in the value here, so that's 1 unity, and we'll give a large area. So the reason why I'm giving a large area here is that I don't want to consider the actual deformation in the columns. I'm more concerned with the deformation in the beam itself rather than the columns. So I'll give a very high stiffness to axial stiffness to the columns, so that it gives you the deformation in the beams prominently. So give the section a name. So that's section 1, or let's say EI, and apply. And the second one has 1.5 times EI, so I'll just change this to 1.5 and just name this as 1.5 times EI. Okay. And close this. Okay, so now how to make sure that all these are assigned correctly. So we can look at the works tree again. So you see that in the sections section list, if you double click on the first section, everything is highlighted. That means EI has been assigned to all the sections, all the elements, which we don't want. We want to assign 1.5 times EI to the right half of the structure. So what we do is use the selection tool and simply create a window from right to left, just intersecting these two components, the column and the beam, and then drag and drop the 1.5 times EI section property. And now if you double click, you can see them quite easily, which section is assigned or which property is assigned to which part of the structure. Okay, so just I'll pause here. I'll try to answer one of the questions being raised by John. He has asked that can we ask the software to give optimum sections to be used? So that is basically the design that comes under the design part. So yes, we can, and I will show you a simple example of that particular optimization, and you can see that how the software will automatically tell you which is the economical section for your structure. So right now I'm just focusing on the analysis. So just after I finish this, I'll take you through an example quickly to show you that. Okay, so now we go towards the boundary conditions. Now again, this is a 2D example, two-dimensional example, so make sure that it is XZ plane, and depending on this XZ plane we'll define the boundary conditions. So we'll select this node, this one here, and this one here, and DX and DZ, which means pinned supports, and apply. Okay. Now we can start defining the loads. So what I'm going to do is I'll name the different load types with different names so that I can separate out which one is settlement and which one is horizontal load, which one is vertical load. So just go to load static load cases and start with vertical, say user defined add. Actually, let me take a case of the dead load, modify, because I'll also show you how the software generates combinations as per the design standards, as per British standard or Euro codes. And then say wind load, for example. So we select wind load, and then we have settlement. Okay, which I'll take as say live, for instance, add. Okay, now we'll assign values. So 16 kilonewton and 20 kilonewton applied at these nodes vertically. So go to loads, nodal loads, and we'll select this node here, vertical load case, -16, apply, and -20 on this one, apply. We can look at the load values by simply displaying from the tree menu here, display. So that's the load value 16 and 20 kilonewton. Then we will apply the horizontally uniformly distributed load on this particular column, which we will name as wind load. So we'll select element beam loads for this case, element beam loads. Select, just save this model, wind load, uniform loads, and the direction is in the X direction. So we'll change it to global X, and make sure we enter the values correctly. So that's 6 kilonewton per meter. So we enter -6 because it is applied from right to left in the negative X direction. Select the column and click apply. So that's the uniformly distributed load. Next thing is the settlement at the two columns. So we are experiencing in this structure a differential settlement. The column BD settles by 3 millimeters and the column CE settles by 2 millimeters. So we'll go to loads, specified displacement of supports, and we want it to settle or the displace vertically, so DZ. Make sure the name is settlement and enter. So since it's millimeters, I'll enter -0.003, so 3 millimeters, apply, and then for this particular node -0.002 and apply. We can check the values, the symbols for the settlement, and we can also look at the values from the tables. So all the input also can be checked by table format. You can look at the values. If I change it to millimeters, so that's 3 millimeters and 2 millimeters at node number 6 and 7. Similarly, you can look at the nodes information, the coordinates of different nodes. So if I right click on nodes, go to tables, it will show me the coordinates. Again, these tables are all Excel compatible, so you can paste the data from Microsoft Excel into the tables here and generate the model data. Okay, so the model has been generated and we can just run the analysis. So analysis is done. And we go to results. We can combine these 3 load cases so that we can check the result for all of them simultaneously. So we go to load combinations and enter a name, say combination, and type is add. Vertical load, we can give some factors, say 1.2 for example, and wind load 1.4. and settlement say 1.3. Okay. Or we can ask the software to generate the load combinations automatically. So auto generate, and we can select Eurocode or British Standard, and based on the type of the design, steel or concrete, just click OK and you get all the different load cases or combinations. Okay, so our objective is to check for combination 1. So let's go to results first and see the reactions. So start with reaction forces and maybe move on to combination. Check on values and apply. So if you see, these are the reactions. What I'll do is change just the color of the output. Change to black and maybe increase the font, right, so it's more clear. And similarly, element output, just change it to okay. So that's the reaction. Again, you can view it in the tables. Then we can look at deformations. So results, deformations, and displacement contour. And here we can switch on legend, deform, and see, compare it with the undeformed shape, apply. So that's the deformation that you're getting. Now this is the nodal deformation, that is deformation at the nodes. If you want to look at the real deformation, that is you may have some curvilinear type of profile here. We can click OK by selecting real deformation. Maybe scale it a bit so it will be say 4 times, for example. Okay, so you see that this particular node has undergone slightly more than 3 millimeter settlement. The units are in millimeters. Okay, that's because the column has some finite stiffness, and because the vertical loads are applied on the beams, so it takes into account the displacement of those vertical loads as well as the displacement settlement of the column itself. Okay, so that's the displacement that you're observing, and the next thing is forces. Now for forces, the finite element software generates the forces about the local axis or the neutral axis of the beam. So that means we need to check which is the local axis of a particular beam. So when I go to forces beam diagrams, I have got several options which says Fx, Fy, My, Fz, Mz. What do they exactly mean? So for this we need to look at the local axis, and I will just delete this diagram from view. So click on this button here, so initial view, and let's look at the local axis now. So click on this display option, element, local axis, click OK, and these are the local axis. So when I'm looking for axial force in these beams, I will be concerned with Fx. As you can see, the red lines, these are the local axis X, and they are in the axial direction for the beam. If I'm looking at bending moment, I'll be looking at My, which is the local axis which bending about the local y-axis. So keeping this in mind, let's look at the forces force diagrams. So beam diagrams and maybe say combination, solid fill, exact, okay, and maybe first of all axial force, legend, and just I'll change this to kilonewton meters and apply. So you see the values in the legend, the colors indicate different values. I'll just make sure the legend is in a fixed format, so it's easily interpretable now. You can also plot the values or display the values on the screen. So you see positive, which negative, which means compression. Okay, so you have compressive force, axial force. Then if I look at the shear force diagram, Fz, so that's the shear force. So you have a linear variation here on this column because of the uniformly distributed load applied, and here you have constant shear force because of the point load applied. Then My, which is the bending moment. Let's see how the bending moment looks. So that's the bending moment shape, bending moment diagram, and the different colors indicate the different values. We can look at all the results instead of the absolute maximum at a particular element. So this is results at each and every point, and you see there's a parabolic shape here because of the uniformly distributed load. So that's how we can quickly see the results of a statically indeterminate structure. Of course, this is in 2 dimensions. As we increase the number of dimensions, we go to 3 dimensions. The complexity increases and manual calculations no longer remain handy. So that's where the software really comes into picture. So I'll just quickly show you an example of the statically indeterminate 3D structure, and in that particular structure I'll take up the question of the optimization of the steel sections. So let me just open up the presentation again. That's a 3-dimensional 2-bay frame analysis. So I won't be modeling exactly the same structure, but what I will do is model a similar structure just to save time, just to give you the gist of how to model this kind of a structure. So the element types that we are going to use are beams and truss elements, beams for the columns and the beams, and truss element for the bracings. The structural system has a moment resisting frame, and we have a lateral resisting, load resisting system in the form of bracings. Bracings are provided in both along the X direction and the Y direction because we want to resist the wind loads in both the directions. Then loads that are applied, we will look at how to apply floor loads. We know that normally for moment resisting frames we don't model the slabs. So we model the slabs basically as, we assume the slabs as loads acting on the beams. So the loads are either distributed in a two-way or in a one-way fashion. And we'll look at how to deal with such kind of roof loads or slab loads without actually modeling the slab. And this is a 3D structure, so fairly complex when it comes to manual calculations. So let's see how the software does it. So I'll again open up a new project. Okay, and what I'll do is this time model a column quickly. So structure wizard, column, say the column is 3 meters high. No, say more than that, say 4 meters. 1 times add, base is fixed. Let's say material 1 and 1. Click OK. That's the column. Now I'll copy this column further in the X direction and also in the Y direction. So just select all. This is used to select all the elements in the view. Go to model, elements, translate. You can also access all these features by simply right clicking elements and translate. Okay. Now we want to copy in the X direction, so type in X in the X direction, say 4 meters and say 2 times intersect node element and apply. Let's change to the isometric view. So we have 3 columns now. Now we'll again select all these columns. So select all, and this time we'll copy in the Y direction. So what we will do is instead of equal distance, let's use the unequal distance option and see what it does. So just selecting Y here, and in the unequal distance I can actually type in different distances. So basically if I want columns at 3 meters and then I want another set of columns at 4 meter intervals, I can type in like this 3, 4 and click apply. So you can look at the view now. Now you've got columns 3 meters apart and 4 meters apart. How do I know if the distances are correct? Well, you can measure the distances from query nodes, or simply press F4. So if I say query nodes and just click or snap on 2 points, say this point and this point, the distance will appear up on the message window. So that's one of the ways you check the distances and make sure your model is correct. Now I'll just simply model the beams. So right click, elements, create elements, and make sure I've selected general beam and simply snap on the nodes and start and end nodes. Now you will be asking the question that what about the node here? Does the beam consider this node? Well, it does, because we selected the intersect node element option here. So when we select the start and end points, it automatically intersects the beam in 2 parts. We can confirm this by looking at the element number. You see it has got 2 element numbers, so it's basically divided into 2 parts. So whenever you have an option which says intersect node element in the finite element software, you can simply click on the start and end points, and it will automatically divide it at the intersecting node. Okay, we do the same thing for the remaining beams here. Okay, and just here, so just repeating it, these locations. So slightly different from the figure which I showed, but it serves the same purpose. We can look at the forces for this structure as well. Now the next thing is we want for most of the lateral load resisting systems, we model the bracings, assuming the bracings to be completely taking all the lateral loads, so that the columns and the columns don't have excessive shear forces. So we model the bracings, and we also assume that the beam column connections are pinned. So there is only the vertical load effect on the beams, and the columns, in the columns we don't have any excessive moments coming from the beam column connections. So that's one advantage of a pinned type of beam column connection. So we will be modeling a pin type of beam column connections here, and we'll make sure that it works as we want it to work. So just to undisplay the element numbers, I will first of all start with modeling the bracings. So elements, create elements, and for the bracings, as I mentioned, I'll use a truss element because I don't want bracings to take any moments. Only the bracing should always be only in compression or in tension. Now, when I'm modeling the bracings, I need to check off this option because I don't want the bracings to intersect, because bracings normally, if I have a X-type bracings here, they normally overlap each other instead of intersecting. So just click and give one bracing here, and maybe another one here for the X direction. Okay, and you see there is no intersecting node, so that means these are all one member. Okay, you can give some more here, for example. Okay, I won't be giving, maybe another one here, but yeah, let's not cover the entire thing, otherwise there will be no space to enter this structure itself. Okay, so now we will make sure the beam column connections are pinned. So we go to model, boundaries, and we go to beam end release. Okay, so the way it works is you just specify which end of the beam you want to release. So whether it is pinned, that is both ends, pinned fixed, that is the start end, only pinned, fixed pinned, the end of the beam pinned, or fixed, which is actually no pin connections, it's a rigid connection. So I'll just explain to you how to decide which is pinned, fixed, which is the start and which is the end, basically. So again, we'll go back to the local axis system, element local axis, and we'll look at only the x-axis, x local axis. Okay, and we see that the x local axis goes, it points towards that direction, in the positive x direction in this case. So that means the start of the beam is this particular node. I'll just display the node numbers. So node number 14 and node number 16 is the end node. We also call the start and end as I and J, as shown in this dialog box here. So if I say pinned fixed, that means this end is pinned, this is fixed. If I say fixed pinned, then the latter is this end is pinned and this end is fixed. But here we want all beam and column connections to be pinned. So what I will do is make sure everything is pinned wherever, because all the ends of the beams basically intersect the columns. So just unselect all and we'll try to reselect everything. Right, so to quickly select all the beams here, what I'll do is use this option, select plane, XY plane, and just click on any point on this plane to very quickly highlight all the beams, and just click apply. So now you have got these dots here which represent the pinned connections. So these members are now pinned. The next problem is the supports. So we want fixed supports, and we have fixed support over here in the first column. So what I'll do is make sure every sub column has got fixed supports. So boundaries again, supports, and make sure D all and R all, which is basically restraining every single displacement and rotational degrees of freedom. So the structure is not allowed to rotate at these nodes, not allowed to deviate or displace. So just restricting everything, and click apply. So it's a perfectly fixed support. Now sometimes what we also do for sometimes you may want to input the actual soil parameters for the supports, and that is the stiffness of the soil. So ideally speaking, we analyze with fixed or pinned or roller supports, but no such support exists. Every support in nature has got some finite stiffness to it. So to deal with such kind of stiffnesses, which we normally come across in case of soil, we go for boundaries point springs. And what we do is the procedure is exactly same as normal kind of supports. We just select or highlight a particular node and make sure we enter the stiffnesses in the X and Y direction and the Z direction. So say if the soil has got 10,000 kilonewton per meter of stiffness in the vertical direction, we just enter the value here, and we enter corresponding other directional stiffnesses here, and then the result is that we are allowing the column to deform slightly, that is settle slightly, and at the same time we are also giving it a restraint. So it is not a perfectly rigid support, but you tend to simulate the accurate situation which happens on site using the spring supports. So just save this model as 3D structure. Okay, now this is a highly indeterminate structure, so materials and sections play a very important role. We need to make sure that materials and sections are properly assigned. So let's go towards model, properties, material, add. So we will be focusing on steel design for this example. So let me just only input the steel properties. So that's steel S355 and click OK. S355, which is the yield strength of steel, is 355 megapascal. Then we go to sections. Now we'll define three kinds of sections in this example. One for the beams, one for the columns, and another one for the bracings. So add, and for the columns we'll go for I section universal columns as per the British standard. Let's say PS 493, and scroll down and we have universal beams, universal columns here. So let's say take the heaviest one, this one, and if you want to edit anything here, you go to user tab and edit the values. You can look at the calculation results from here. So the procedure is fairly same. We'll name it as column. Apply. So as you see, everything is assigned with the same section because we didn't assign any material to start with. So the first section is the default section for every element. Next thing is the beam. So again, I section. Now make sure when you apply a section, the dialog box stays open, so you can keep on adding more sections. So again, for the beam, let's go for another heavy section, say this particular one, and maybe enter the name as beam and click apply. So we have a beam section, and then for the bracings, we'll go for a pipe section. That's the pipe section, name it bracing, and in the British standard we call it the circular hollow section. So let me select one of them, say this one for example, and click OK, and I'll close this box. Okay, now make sure that all the sections are correct. So like I said in the previous example, we can simply select a particular set of elements. So I'll select the beams at this level, right, and just drag and drop the beam section. So that is the beam section. I'll quickly undisplay all the element local axis so it's clear. Okay, and the bracings, so what I'll do is make sure I select all the truss elements. So double click on truss, so all the truss elements are highlighted, and drag and drop bracings. So these are my bracings now, have been assigned correctly. Now the next question that appears is from the display is that why are these beams and columns connected center to center? What if because in reality the top of the beam should be exactly matching with the column center. So why is the beam offsetted like this? And that's because for every section in the reference line always represents the centroid of the section. So in order to offset the section slightly, we need to manually force the section to shift it by some amount top or in the bottom direction. So for these beams particularly, we'll just right click on beams, go to properties. As you can see, the centroid is the default section reference line. We go to change offset and just enter center top here. Make sure it's extreme fiber. So you can enter the distance as well manually. Extreme fiber will automatically shift it to the top. And now you see a red dot here which represents the new reference line. Click OK and you will see the beam shifts automatically. So that's how you create the offsets for this type of structures. So now we've got the main model generated. Let's now focus on the loads. So I'll begin with load, static loads, say dead load, add, then live load, add, then wind in the X direction, wind load on structure, and wind in the Y direction, add. So close this dialog box and start quickly defining the loads. So we'll start with self weight first. Self weight, it's a kind of a dead load. So we'll select dead load here and make sure Z -1. -1 in the Z because self weight acts in the gravity direction, which is the negative Z direction. Add and close this dialog box. Then we go for the wind loads. So wind loads will act on the column top and bottom nodes. Basically, let's apply the wind loads as the uniformly distributed load on the columns. So what I'll do is select all the columns here and go to loads, element beam loads, say wind load in the X direction. This is the front view, so X direction, global X, and the value is 10 kilonewton per meter, for example, and apply. So that's the wind load applied. Next thing, we'll do the same thing for the Y direction. So just select all the column members here, global Y and WY, and say -10. Apply. Okay, so we have defined the wind loads. Now let's define the floor load on the top, which I was mentioning earlier. So for the floor load, we'll define the load coming from the slab in the form of dead loads and also live loads. So we select define floor load type, and say give it a name roof. Dead load, enter the values, say -4 for example. Live load, say -3 kilonewton per meter square, and add. Then close this and go to loads, assign floor loads. Make sure you've selected roof, which we defined just now. Distribution type, two-way or one-way distribution. Let's go for two-way. Direction is global Z, and just we need to connect the nodes like this, and you see the loads are automatically applied, distributed in a two-way fashion. Okay, since this is a square type of a plan, you can see here you have arrangement like this, and here you have rectangular type of distribution. Okay, that's how we apply the floor loads, and once we have done this, we can simply click on perform analysis. As analysis performed, and we go to results, combinations. We want to do the steel design, so we'll go to steel design tab and go to auto generate, say B British Standard, for instance, BS5950, and click OK. And we have got all the British Standard ultimate limit state combinations here. Okay, so I'll close this dialog box and we'll look at the results now. So starting with reactions, let's see for one of the combinations. These are the different reactions or the supports. You can look at the moment reactions as well. These are the moments that you're getting at the reaction at the supports. Deformations, let's look at the deformed shape, maybe displacement contour, deform, legend, apply. So that's how it is deforming. We can look at it in a more realistic manner. That's how it deforms, each beam deforms. Let's look at the bending moment diagram now. So that comes under forces, beam diagrams, My. We discussed that how to decide Y, X and Z. Apply, just make sure solid fill is checked. So that's the bending moment diagram. Exact will give you a more parabolic shape. Now since the connections were all pinned, so you will see that there is no moment in the column. All the moments are only restricted in the beams. So that means our analysis is correct. Our assumptions are correct here. Now what if you were interested in looking at at one of the frames at a time? Because we don't normally, for report purposes, we won't be looking at all the elements at the same time. We look at the one of the frames at a time. So what we will do is select a particular plane. Let's say it's using 3 points. So select the central one like this. Okay. Just a minute. Yep. So we can, let me just select it. Just change it to the initial view. Yeah. Okay, and just change this to the line view and say side view, and just select the elements here and click on this option which says activate. So this will only display this particular frame, and now I can look at the results for only this frame. So go to beam diagrams, say axial force in the columns, values, legend, apply. That's the axial force. Shear force, apply. So that's the shear force. Okay. Then moments in the minor axis. That's a little bit more moment in the minor axis. Okay, and I'll now activate the entire structure by clicking on this, activate all. That's the entire structure in view. Now, what if you were to look at the results within a beam, how the stresses change, or how the different displacements change within a beam element? Because you don't have nodes here, so normally finite element results always are displayed on the nodes. So to see this kind of situations, we can look at beam detail analysis. So what we do is click on this option and click on this box here, and just simply select one of the beams which we are interested in. So say just click on this beam. Okay, so the diagrams will appear. So this is the displacement in the Z direction, vertical displacement. You have a slider here. If you move it, you would be seeing the values changing here. Okay, so that's the value of the user value. You can also look at sectional stresses. So if I change to section, you can look at the cross-sectional stresses by changing, just locating the points. That's the neutral axis. You can also look at the, that's the von Mises. You can look at the normal stresses. So that's the normal stress, axial plus bending. You can also look at the shear forces, tau xy, which is the shear force in the longitudinal direction. Tau xz is the shear stress in the vertical direction. So that's the shear distribution. As we know that most of the shear, if you see the shear distribution is taken up like this. Okay, so more flow in the web. Okay, now we've seen the results. Now we can just quickly design the elements. So for designing the elements, we go to design, Set up the design parameters, steel design parameters, go to design code. Let's design it as per British standard. Okay, we can select if we want to do the lateral torsion buckling check or not. So I'll just keep all beams and girders are laterally braced. So I'm not considering any lateral buckling. And go to design and just simply click on steel code check. And it comes up with a table. Blue means the steel sections are passing the check. And these values 0.03, 0.151, 0.075, these are the utilization ratios. So combined ratios as per the axial and bending resistance. So if I just select one of them and go to graphic, it will give me a list of the checks it has performed. So you see this is the design information, the section taken, and these are the checking results, slenderness check, axial resistance, bending resistance, and so on. You can also go through a full step-by-step check by clicking on member and maybe say just click on connect model view and just select one of the members by clicking on it and go to detail. Sorry, just make sure you select one of these columns and go to detail. So the detail result will actually show you the full step-by-step calculation, which looks like this. So it shows the full step-by-step code-based calculation, which is good for you to manually verify the code checks. Okay, so what equations have been used, and we also have a design tutorial which shows you which equation has been taken from which clause of the code, so it's easier for you to reference. Now say if this is the code check, that's fine, and the major challenge for the engineer is to optimize a section to say that say for example this column section is very clearly we can see only 3% is being utilized, so we should this is highly uneconomical, so we would like to optimize this particular section. So we can simply go to just click on this particular column section, go to change, select some other section, say from British standard, some other I section. You can enter the utilization that you want, say between 80% to 100%, and search satisfy section. Now the software comes up with a list of sections that you can select from. So it comes up with say these many sections, select one of them. But mind you, this is the only the ULS check. So this optimization does not involve the SLS check. Okay. So now you see after the correction, the new combined ratio is 85%, which is good. Now you can update it. So right now the analysis results are same. You can update it, and analysis results will be deleted. Perform a reanalysis and perform a recheck. So forces will be again redistributed, and your section is changed in the main model itself. And if you check on graphic, you have some other section in the view here. So that's how you optimize a section. There is also a provision for optimizing the entire model at a time. That comes under the steel optimal design. So here you can simply select which sections you want to optimize, what kind of plate thicknesses you want for the top flange, bottom flange, web, and just run the design and analysis. It will run some iterations and come up with the most optimized section. Okay, and text report, save. Okay, so that's what it comes up with. You see the original section was this one, and after optimization this is the section, and you've got a massive you've got a reduction in weight of the beam and the bracings basically. So you can look at graphically as well how the weight varies. So that's the that's the red line is the original summation, weight summation, and the line below is the new weight of the structure after optimization. So that's how you optimize a particular section. I hope that answers your query, John. And if you have any query, then please let me know. Okay, so the next, just quickly to sum up the presentation, I'll just go through some simple examples of buckling, because this is another aspect, the stability check. We have looked at the strength check, we have looked at the stiffness checks. Now we are looking at the buckling or stability checks, which is the third most important parameter for the design. So for the buckling checks, we basically have two types of buckling. One is the axial buckling, which is also defined in the textbooks as the Euler buckling, and the other is the lateral torsion buckling. So we'll go through both these checks, and both of these are very important for steel sections, especially in the UK, in the building industry and in the bridge industry. Both these buckling types are very critical in the structures, as most of the structures are made of steel. Okay, so starting with the axial buckling, we'll just look at the simple column and how it buckles, and the support conditions are pinned and pinned at the base and roller at the top. So we'll go to MIDAS Gen again, go to new project. So you can click here also to start a new project, and I'll go to model, structure wizard, column, to generate a column. So the important thing in the buckling analysis is that the more number of elements you have, the more accurate the analysis becomes, because the buckling analysis works on the concept of generating works on the eigenvalue analysis basically. So you have to have a certain number of elements and nodes to get the maximum response out of all the column or beam elements. So the more number of divisions you have, the better it is. But again, the more divisions also lead to slow down of the analysis process. So you have to judge by taking several such cases and see when you reach the optimum level. So for this case, I will take a 10-meter high tall column and divide it into 10 sections. So I take 1 meter as a distance interval and repeat it 10 times. Add and pin the base, so make sure it's pinned. Okay, and material type we can select from here. So just quickly go to add, just select steel 355, section, add, and maybe just I'll select universal column again. Okay. Material and section types are important because for the axial buckling, as per the formula by Euler, it says that the fundamental mode of the critical load at which the column or the element buckles is given by is dependent on the modulus of elasticity, the moment of inertia, and the overall length of the member. So keeping these things in mind, we need to enter the materials and section correctly and click OK. And the other thing is, it also depends on the support conditions. So different support conditions may give you different effective length for the buckling. So we'll see how the buckling the boundary conditions affect buckling through this analysis. So the first case that I'm taking is print support at the base, and at the top I'll give a roller support. So boundaries, supports, and maybe only restrain the dx, degrees of freedom, and maybe dy, and apply. Okay, now I will apply a load at the top, an axial load. So loads, just name it, say P, for instance, user defined, and select the top node here and nodal loads FZ, because it's in the vertical direction, say -1000. Okay, and the software will tell me, so this is an initial load I have applied, and the software will tell me what extra factor should be multiplied with this particular load, such that the column buckles. Okay, so now we set up the buckling analysis control, buckling analysis, a number of modes we want. So let's go for 10 modes and add. Okay, now run the analysis. I'll just save it. Oops. Okay, we'll reduce the buckling modes here, maybe 5. Okay. Okay, make sure that this is boundary conditions are entered correctly. Right, Tx. Small. Okay, so yeah, so I will choose the boundary conditions here for the 2D for the 2 dimensions only, just to check the modes in the X and Z. So results, and we go to buckling mode shapes and select mode 1 and check on legend, contours, and maybe undeformed shape and apply. So that's the first mode of buckling, and the factor which you see here is 15.93, so approximately 16. So 16 times the original load. If you apply, then the column will buckle in this fashion. And if we scroll through other buckling modes, say mode number 2, that's the critical load factor increases. Mode number 4, so and so on. And the more number of elements you have, it will give you a more accurate result for the buckling load factor. We can also look at the animation of how it buckles. So just click here. So that's how the column is buckling under the axial load. And if go to multi modes, and you can look at the several modes at the same time. So like this. Okay, and you can compare the mode shape factors, critical load factors. Okay. All right. Now let's see what difference it makes when we have a fixed support at the base and the top is free. So I'll delete the support at the top. So delete, and make sure the base is completely fixed. And apply, and run the analysis, and see the buckling mode shape. See, now the mode shape changes, and you have the factor required is very less compared to the previous case. So it's 4, only if you apply 4 times the load, and the column will buckle in this fashion. Mode number 2, then 3 and 4. So boundary conditions, material properties, section properties, and the overall length of the member, they all affect the how the system buckles and at what load it will be buckling. So that's how the actual buckling can be taken care of using the finite element software. And finally, we'll look at the lateral torsion buckling. So for lateral torsion buckling, to capture the lateral torsion buckling, we need to have a shell model, and because we want to see the deflection or the variation of deformation of the top flange relative to the bottom flange or the web. So to see all these things, we need to model each and every component as the plate elements. So just to quickly show you how we can do that in the software, I go to File and New Project, and I'll just simply generate an I section, and we'll look at it in terms of the lateral torsion buckling. Okay, so I'll go to Nodes, create a node, apply, okay, and select the node, create a line, okay, in the Y direction, apply, okay, and select the previously selected node by using this option and create another line. So this is the top flange, and now using this node I'll drop another node in the vertical direction, another element in the vertical direction, 1 meter web. Sorry, it should be the other way around. So -1. Okay, and now we'll copy this same top flange downwards. So just select, right click, elements, and translate, and we can measure the distance directly by clicking on the top and the bottom point here, and intersect and node an element and apply. So that's the shape of the I section. Now we will divide these lines further. So change it to the side view. So divide these elements, right click, elements, divide. So divide in 2 parts. Divide this one in, say, 8 parts, for example. Apply. Okay. Now using these lines, I'll create plate elements in the X direction. So select all, right click, elements, extrude, and make sure this is line to planar. So we are creating planar elements from line elements. Okay, and we'll copy it, say, in the X direction, 0.1 meters, and say 20 times, right? So we have got beam, 2 meter beam, which is completely made of plate elements. Okay, now we will apply the loads on the supports. So just changing it to front view, selecting the bottom flange here, go to model, boundaries, let's assume a simply supported case. So pinned at this location and roller in this location. Okay, and the top will be loaded with a uniform pressure load. So basically what we want to achieve is compression at the top and tension at the bottom. So since the top is in compression, so the top flange and some part of the web will buckle, and we want to see that effect. So loads, create a load case, say pressure, and let's select the top flange, loads, and apply pressure loads, and this is in Z direction, say -100, apply. Okay, and the same way we define materials here. So say steel as 355, and since these are plate elements, we have to define thicknesses. So we go to properties, thickness. We define 2 types of thickness, one for the flange, so that is 0.05 or 50 millimeters, and the other for the web, which is 20 millimeters or 0.02. And make sure the web and the flange thicknesses are correct. So I'll select the top flange and the bottom flange and drag and drop 0.05 and select the remaining like this, drag and drop 0.02. And to see if the shape is or the thicknesses are correct, I can display the thicknesses from display option, plain thickness, click OK and OK. So you can see the thicknesses like this. So now we can run the buckling analysis. So buckling analysis control defines 5 modes, for instance, pressure load, add, and click OK. And the analysis. Okay. So the analysis is complete. Let's look at the buckling mode shape. So results mode shape, mode 1, say undeformed and apply. So you see clearly you can see that because of that vertical load, the beam has buckled laterally. The top flange, the bottom flange being in tension is does not buckle, and the top flange and some part of the web has moved laterally because of the compression. And the force required for generating this kind of mode is almost 7 times the applied loading, which was 100 kilonewton per meter square. So that's how we can do the buckling, lateral torsion buckling check on any kind of structure. So what we need is the or for that matter any kind of local buckling check. So if you browse through the several other modes, you will find local buckling as well in some of the modes. So you see here there is some kind of warping at these locations. So if you model the structure as plate elements, then you have this advantage of taking in this kind of local buckling effects and looking at them in the finite element analysis. Okay, so that concludes this session today. If you have any questions, please you can post it on the questions window. So that's just one of the videos for the lateral torsion buckling. For the FRP beam, we generally, yeah, actually the FRP beam we are treated as the orthotropic with orthotropic properties. So if you have got the equivalent orthotropic properties for the FRP beams, you can consider them in the analysis. So say when you define the material itself, you have user defined, you can go for orthotropic, define the properties in different directions, and we can do the consider those properties into account in the analysis. There's another question which does the software include nonlinear analysis under seismic effect? Yes, we can do such type of analysis using the time. There are different ways. You can either do a pushover analysis, which is nonlinear static seismic analysis. So we have an option here for pushover separately. So you can define your hinges in the beams and apply the incremental loads and do the pushover analysis. Or you can also look at the time history analysis with such kind of nonlinear hinges. So the way it works is you have to idealize the structure, the frame, as a frame with plastic hinges at different nodes, and then apply the time history or the incrementally increasing lateral seismic load, and you can look at the status of the hinge, how the hinge goes into uh, elastic to the plastic zone. So I'll just show you what kind of hinges can be defined here. So if you select, say, Eurocode, you can define this type of Eurocode hinges for different state of the structure. And the software will tell you at which stage in the stress strain curve the node is in. Jimmy Young has asked, does the software do fatigue analysis? Well, this is the frame analysis software, and for fatigue analysis, we do have detailed finite element software, which allows you to input the stress cycle and the strain cycle and gives you the damage life of the structure. So the purpose of this webinar was basically to look into the basic frame analysis and buckling analysis and design features and how it can be implemented for simple frame structure basically. So fatigue analysis, we do have several tutorials on our website. You can mail us at uksupport@midaisuser.com, and we can send you the tutorials. Okay. So if there are no other questions, then I would like to end this session. We'll send you the recording of this session shortly, and also the different documents involving hand calculations and correlation of the hand calculations with the software.